Okay, so we're going to perform the construction of Euclid's Book 1, Proposition 2. That is, to place at a given point a straight line equal to a given straight line. So we're just going to say from the end of some point like A, we want to extend something called AH, the same length as our given segment. We're going to make our given segment BC. So this is what the final construction looks like, and we're going to go back in time and recreate that. So, oof. Okay, so this is what we start with. A, some given point in a given segment. We want something the length of BC like this, coming out of A. By the time we're done, something the same length. Doesn't have to be in the same direction or anything else. And this construction came about because Euclid wanted to show that you didn't need a compass that was rigid like this, that has a little thing in the middle so you can pick it up and move it to do his geometry. I don't know what this person's doing, but this is not a rigid compass, it looks like. And neither is this one. So they pick them up, they collapse, and you're back to square one. You don't even know what you just measured. And we're trying to avoid that problem, or show that it's not even a problem, more or less. So we're going to start with using proposition 1 because Euclid's the man with the plan. We planned this out 47 in advance, or 46 in advance, I don't know, because I've already done one. So. And we have our AB, and following the construction of the equilateral triangle, which is in the previous video. This to intersect both of these, and we'll give it a name. And then we're going to come back in here and we're going to hide these guys because they're just going to create trouble for us later when we start making other circles and stuff. So now we have this equilateral triangle ABD and a segment BC, and we want to extend some length BC from segment A. So let's create some super duper infinite lines because they'll probably come in handy. And way out in the middle of imaginary land, we're going to put a couple points and we're going to give them some names. So they're going to be Tom. Actually, it's going to be E. This one's going to be F. Alright. And from here, we're going to create a circle with radius B, or center B, excuse me, and radius BC. And now from here, we're going to create another circle, but with radius, center D, and we're going to go out to the end, lying on line DF. So we're going to create that little guy right there, and we're going to give him a name. It's probably going to be G. Yeah, real predictable. That's how the alphabet works. Pretty neat. It's kind of like math. And now we have two circles, and they're sharing a common boundary point G, and we're going to make use of that later. But first, let's observe what we've created. We've got this segment BG, and we're going to go ahead and color it. We're going to color it orange. We also have a segment BC that we're going to color orange because they're both radius to the same circle, so they're like twinsies or something. And we have this other radius of it, BA. That's not a radius of that circle, excuse me. But BA is part of our equilateral triangle. We do need these guys to be the same color, so we have some cohesion going on with the unit here. They know who's who and get along. Maybe have a gang battle with the orange segments. But now we have this equilateral triangle, and we have this. And this looks strikingly familiar to something over here. It's blue guy, orange guy, blue guy, and something is not blue. So maybe make a little point here. We can make some observations about this segment and maybe even deduce that we've done what we intended to do. Oh, no. You're going to be a segment and you're going to like it. There we go. We can't color that yet because we don't know for sure. So let's work on a little bit of logic here. D, G, and DH are both radiuses of the same circle. And then So we know this whole thing, the blue-orange is congruent to this blue with gray. Now if we take the blue away from each segment, we know that's going to leave us with, instead of dB, take that out, that leaves you just with BG. And if you take dA out of dH, you wind up with just AH. That means AH must be congruent to BG. We're taking away something of the same size from something that is congruent. And let's zoom out. This is our construction now. So it's a whole lot of words, but it's really quite simple, just showing you don't need a rigid compass because not all compasses were created equal, and Euclid had a very I don't even know the word for that. He's very sympathetic to the compasses that weren't created equally.